Hey everyone, and welcome to Next Gen Manufacturing. Today we are talking about a material that is, and I mean this literally, holding our modern world together. It's in our cars, it's in our power grids, our phones, but you almost never see it. It's time to pull back the curtain on this incredible unsung hero. So let's start off with a little bit of a riddle. What on earth do these three things have in common? You've got a huge insulator for a power line, a pair of super high-tech skis, and the circuit board that's probably in the device you're watching this on right now. I mean, they couldn't seem more different, right? But they all share a secret ingredient, a kind of DNA that gives them their amazing performance. And the answer is epoxy resin. Yep, this amazing polymer is the quiet workhorse behind some of our most advanced technologies. It's incredibly strong, it's a fantastic adhesive, and it's a great insulator. It's the material you turn to when things absolutely cannot be allowed to fail. So here's how we're going to break it down today. We'll start with the magic of epoxy, what makes it so special. Then we're going to dive into the huge challenge of actually working with it. It's a delicate chemical dance. After that, we'll see the manufacturing revolution that finally tamed it, how that process led to a whole new world of products. And finally, what this whole story tells us about the future of making things. Okay, first up, the magic of epoxy. Let's just take a moment to appreciate how deeply this stuff is embedded in everything we do. I mean, just look at this list. The sheer range here is wild. In aerospace, it's used to bond parts of planes together, making them lighter and stronger than if they used old-school rivets. In sports, it's what gives high-end skis and tennis rackets that incredible strength and flex. It's the tough coating that protects giant ships from saltwater. It's the insulator that keeps our power grid safe. And it's literally the foundation that all our modern electronics are built on. It's everywhere. But you know, for all its amazing properties, there was always a big catch. For the longest time, using epoxy to its full potential was just incredibly hard. You see, making something with epoxy isn't like pouring melted plastic into a mold. It's more like conducting a very tricky, very volatile chemical reaction. And this right here is the absolute key to understanding the problem. When you're making an epoxy part, you're not just shaping something that's already there. You are kicking off a one-way, irreversible chemical chain reaction. It's called curing. And for manufacturers, this process created three massive headaches they had to solve. Challenge number one is something called pot life. The second you mix the two parts of the epoxy together, a clock starts ticking. You have this really narrow window of time to pour the liquid and get it into the mold before it starts to get thick and gel-like. If you're too slow, well, the whole batch is garbage. The pressure is on. Then you've got the exothermic peak. Now this is where it gets crazy. That chemical reaction, it generates a ton of its own heat. And in a big, thick part, that heat gets trapped in the middle and can't escape. It creates this runaway effect where the core gets hotter and hotter, causing stress, cracks, and all sorts of defects. It's like trying to control a tiny chemical fire inside your product. And finally, challenge number three, total shrinkage. As the epoxy hardens and solidifies, it naturally shrinks and pulls away from the walls of the mold. If you don't manage that perfectly, your final part is going to have the wrong dimensions, it's going to be full of internal stress, and the surface will be a mess. So, to see how all these problems played out in the real world, let's look at the old school way of doing things, a method called classic casting. Honestly, classic casting was a bit of a nightmare. Because that exothermic reaction started in the hot center and spread outwards, the whole process was just chaotic. That uncontrolled heat created huge internal stress points. The shrinkage led to ugly surface defects, sometimes with these weird patterns that look like ferns. And maybe worst of all, you could make two parts the exact same way and get two different results. It was unreliable and it took forever, which made mass production pretty much impossible. But then came the breakthrough, a true manufacturing revolution. This wasn't just a small tweak or a workaround. Engineers invented a completely new way to solve the curing problem from the ground up. And that breakthrough was a process called Automated Pressure Gelation, or GPA. This technique was developed specifically to get that wild epoxy reaction under control. It was, and this is no exaggeration, a total game changer for next-gen manufacturing. Now, this is the really brilliant part. GPA completely flipped the process on its head. You see, classic casting was this chaotic inside-out reaction. But with GPA, you heat the mold itself and then inject a slightly cooler resin. This forces the curing reaction to start at the hot mold walls and then move steadily and uniformly toward the center.
It turned a chaotic inside-out process into a perfectly controlled outside-in one. That runaway heat problem solved.
And the results were just staggering. The cycle time, basically how long it takes to make one part, was cut by a factor of 10, sometimes even more. A process that used to take hours now took just minutes. This, right here, is what unlocked the door to true mass production of high-quality epoxy parts. The benefits were just enormous. GPA gave you parts with a perfect, smooth surface finish, no more weird fern patterns. The parts were way stronger because they were totally uniform inside. You could make 1,000 of them and they'd all be identical. And get this, the process uses a little bit of pressure to keep feeding resin into the mold as it cures, which completely cancels out that shrinkage problem. It basically solved every single issue with the old method. And that brings us right to our next section, from process to product. Because you see, a manufacturing innovation this huge doesn't just make existing things better. It lets you create entirely new things that were impossible before. Here's a perfect example of that. Before GPA, the big insulators you see on power equipment were made of porcelain. They were heavy, they were fragile, but with GPA, companies could suddenly churn out these incredibly complex and super durable epoxy insulators at scale. It didn't just compete with porcelain for indoor uses, it made it basically obsolete. And that revolution just snowballed. The precision and speed of GPA became the foundation for everything. The complex insulators and circuit breakers that run our power grids, the dense, multi-layered circuit boards in our computers, the incredibly strong but lightweight panels in airplanes, and yeah, even those high-performance skis and tennis rackets that can take a beating and keep on going.
So, after all that, what's the big lesson here? What can the story of epoxy and this manufacturing revolution really teach us about the future of making things? Well, it really boils down to this. Epoxy resin itself had been around for a while. Its potential was there, but it was locked away. The real revolution wasn't the material, it was the process that finally set that potential free. The biggest leaps forward don't always come from discovering something new, but from figuring out a brilliant new way to use what we already have. And that leaves us with a pretty big question to think about. The GPA revolution happened decades ago, so what are the equivalents today? What quiet innovations in things like 3D printing or biotech or robotics are happening in labs right now, getting ready to unlock the potential of some new material and completely reshape the world of tomorrow? Now that is something to think about.